I made the mistake of upgrading to the new version of Mac OS, and it killed my board. So I'm not going to be able to write on the board. So all the more reason you would want to have this table in front of you, because guys, this is really the distillation of the really important stuff that you've got to be able to do as a result of chapter 19. Of course, we're not there yet because we haven't talked about Gibbs free energy. But guys, the way the day is then going to play out, we are going to first of all take enthalpy and entropy and bring them together, and that's called Gibbs free energy. And then once we've brought that concept together, we are then going to answer the question, what reactions are spontaneous? And guys, we can answer that question emphatically. It's not tends to be, it's not often is, it's none of that. It's, yeah, this thing is spontaneous, or no, this thing is not, because Gibbs free energy will tell us with certainty whether or not a reaction is spontaneous. And then we've got to be able to talk about conditions, and that's where that table brings us to. You got the idea? Okay, so guys, let's do this first. In summary, here's what we know. This is chapter 5 and chapter 19 in 2 sentences. You ready? Chapter 5. Chapter 5 was all about heat and enthalpy. And guys, what relative to heat and enthalpy, what reactions tend to be spontaneous? Exothermic reactions. So guys, we established that in chapter 5, that reactions that have large negative enthalpy changes, that's code name for exothermic, those tend to be spontaneous. Then guys, over the last couple days in chapter 19, we brought in the idea of entropy. Increasingly, we're becoming comfortable with the idea that disorder is really a thing that drives processes. And we said this. We said reactions that tend to be spontaneous cause increases in the entropy of the system. And guys, you'll notice that we defined the system, because we know more universally that if a reaction is spontaneous, it has to cause an increase in the entropy of the universe. But typically for spontaneous processes, that occurs because of an increase in entropy of the system. So guys, let's pause there, because that's a wonderful review of where we are right now. We're talking spontaneity. We understand that reactions that tend to be spontaneous are exothermic, chapter 5, and causes increase in the disorder of the system up till now in chapter 19. So anything you want to explore there? Go ahead. No? You're just stretching. Anything you want to look at there, guys? Okay, so now, guys, let's bring this back to the quick cold pack, because now we have a problem, right? Is the reaction that takes place in the quick cold pack spontaneous? Yeah, but which one of these 2 bullet points does it violate? Top or bottom? The top one, because that's an endothermic process, but we also know that it's spontaneous. So we understand, guys, that if everything lines up, and if a reaction is exothermic, and if a reaction causes an increase in disorder, it will always be spontaneous. Now, guys, do this in your head. What if we have a reaction that is endothermic and causes a decrease in disorder? Think about that. If we have a reaction that is endothermic and causes a decrease in disorder, will that reaction be spontaneous? Never, because both of those characteristics work against spontaneity. So the idea is this: if energy goes out and screwed up goes up, it's going to be spontaneous. If energy goes in and screwed up goes down, it'll never be spontaneous. But what about these? What about the ones where one of the factors favors spontaneity and the other one doesn't? What if we have a reaction that's exothermic but creates a decrease in disorder? Or what if we have a reaction that's endothermic and creates an increase in disorder, like the quick cold pack? How do we break the tie? And guys, the answer is this, and you don't need to write this down, but the answer is we need a way to predict spontaneity that brings these two factors together. And that is what is called, and this is where you want to pick up your notes again, that is called Gibbs free energy. Sometimes you'll see it just called free energy. Yeah. In the system. Not in the universe, but in the system. So we have that happen all the time. Life is a decrease in disorder, right? We take all these crazy molecules, put them together, and get us, and we're pretty organized. So yeah, no, but I'm glad that you're picking at that, because no, when we say there has to be an increase in disorder, we're talking about the universe, but here we're talking just about the system. Go ahead. Okay, yes. It's decreasing. Yeah. So if that process is spontaneous, then we know that there's an increase in disorder somewhere else. I don't want to dig into this too much because given your guys' propensity to run down rat trails, I really don't want to get into this conversation because you guys will spend the rest of the day talking about it and fail the test. But there are certainly, we can talk about that idea of transferring chaos, but I'm scared to go there with y'all, so I'm not going to. So, but your thought is good. Yeah, so we're okay. So guys, Gibbs free energy is simply a thermodynamic function that brings together enthalpy and entropy. Finally, thank goodness, an abbreviation that makes sense. Guess what it is? G. Enthalpy is H, entropy is S. Finally, it makes sense. They're giving us the G. So guys, Gibbs free energy is abbreviated G. Now, actually, you know what? We can do this. Empirically, guys, this is how these come together then. The Gibbs free energy of a system is equal to the enthalpy of that system minus the temperature of that system times its entropy. And guys, these temperatures have got to be in Kelvin. But that's not how we're going to deal with it. We're going to deal with it this way. We're going to talk about changes in Gibbs free energy as processes take place because we are going to use this predictively to figure out whether or not reactions are spontaneous. But so long as we're at it, we may as well grab our AP equation sheet and find this equation on the equation sheet to make sure we can locate it. So you got it there. Delta G is equal to delta H minus T delta S. You'll notice, guys, that there's also two other forms of this. One that says delta G is equal to negative RT ln of K. We'll talk more about that when we talk about kinetics sometime after Christmas. And then, guys, the final one says that delta G is equal to negative NFE. That is actually the Gibbs free energy change for an electrochemical cell. This will actually be the last equation that we talk about this year. So in April, when we cover delta G is equal to negative NFE, we're done with this class. Then we just study for the test. It feels like it's a long ways away. It's going to be here before you know it. But guys, the form of this that you need to know right now, which is also on the board, is delta G is delta H minus T delta S. You guys all found it? Go ahead. No, yeah. Okay, so guys, delta G is equal to delta H minus T delta S. I would really much rather write this on the board, on the screen, but I can't. So you've got this, I've got it. Guys, here's the way the conversation's going to go for the rest of the day. You ready? We are going to agree together, for the sake of this conversation, that spontaneous is good. Okay, we're going to talk about the tension between good and evil. So you ready? Spontaneous is good and non-spontaneous is bad. Do you get the idea? Spontaneous is good, non-spontaneous is bad. Now guys, with that in mind, join me at this equation. So spontaneous is good. Feel free to write this down with me. We're setting up a conversation that we're going to finally wrap up with at that table in the book. Now guys, do this with me. And it's actually on the screen as well. If you need a reference, you can look here. So have this conversation in your brain. What delta H values lead to spontaneity? What delta H values are good? Negative delta H values, right? Because what do negative delta H values tell us about the process? Exothermic. Now, what delta S values lead to spontaneity? Positive delta S values. Those are good. They lead to spontaneity. So now, guys, bring that thought together. What delta G values must then be good, must then indicate spontaneity? Negative? Oh, now I'm hearing both. So let's do this. Okay, so guys, rather than guess, let's talk about it. So delta H values that indicate spontaneity are negative, right? So let's isolate that and agree upon that. Delta H values that are negative indicate spontaneity. Now, let's isolate and talk about this second term. Notice what we've got. We've got a negative sign, which is a subtraction sign, but I think you're comfortable enough with algebra that you understand that that's really plus a negative. So, this is temperature. What did I tell you the units have got to be? Kelvin. And what do you know about Kelvin temperatures? What can't a Kelvin temperature be? Negative. So these have always got to be positive. So temperature is always positive. Now let's look at delta S. If delta S is tending towards spontaneity, you've already agreed that that's a positive sign. So T is always positive. Positive delta S's indicate spontaneity. So we've got a positive times a negative, making this negative. Now, if this is negative, and that tends towards spontaneity, and if this entire term, positive, negative, is negative if tending towards spontaneity, what values then for Gibbs free energy would we expect would indicate spontaneity? Negative values. Guys, that's it. Bottom line, no more guessing. If you want to know definitively, and you do, or at least you do if you want to pass the AP test, if you want to know definitively if a reaction is spontaneous, the only never fail you indicator of spontaneity is Gibbs free energy change. If it's negative, it's spontaneous, end of story. Get it? Go ahead.
So does that mean that if it is endothermic, then it'll always be a smaller number than the other?
So if this is, and here's the way the conversation is going to go down. If this is endothermic, this is positive, and that's bad, right? This is bad. This doesn't lead to spontaneity. So what would have to be true of in order for the whole thing to be spontaneous, what would have to be true of this term? It would have to be more negative than this is positive. Yeah, and so functionally what that means is that either this would have to be a process that creates very large changes in entropy, or we'd have to get it hot. And that's what we're going to talk about at the end of the day. Yeah, go ahead.
So is the temperature
It's the temperature at which the process is happening. So for example, we've gone back to what, so did you guys hear the question? Is that final temperature or initial temperature? And the answer is the temperature at which it's taking place. So for example, we talked about ice melting and turning into liquid water. So if the process we're talking about is ice turning into liquid water, that is not, let's do boiling. So water turning into steam. So that water turning into steam process is not spontaneous at temperatures below 100. It is spontaneous at temperatures above 100. And what we're going to do at the end of the day today is we're going to calculate where that tripping point lies. At what temperature does a process become spontaneous? Correct, of the environment. But that's also the temperature of the system, right? We're assuming that they're in thermal equilibrium. Yeah, good. Are you guys okay with the idea then? Okay, so what then functionally does Gibbs free energy do? Well, guys, the sign of Gibbs free energy tells us spontaneity. So you ready? Let's see if you figured it out. What do you know if delta G is negative? The reaction is spontaneous. Always? Always. Guys, there are very, very, very few alwayses in this class. You just got one. If delta G is negative, it's spontaneous in the forward direction. What that means is in the direction is written. Now, I'll bet you can come up with this even though we haven't talked about it. What if delta G is 0? What do you suppose that system is doing? Good, it's at equilibrium. Yeah. Now guys, this is a deep thought. I'll let you catch up because we need to talk about this. What about this? What if delta G is positive? The reaction is not spontaneous in the direction that it's written. It is spontaneous in the other direction. You get the idea? So if we calculate the delta G for a process and we find out it's positive, what that means is given where we have the reactants and the products, that process is not favored. It's not spontaneous. But if we flip the reactants and the products around, then the sign of delta G changes, and now that process is spontaneous. So it's spontaneous in the reverse direction. Yeah?
Does that mean that any reaction can be spontaneous?
It means that any possible change has a direction that it can go all on its own. So for example, if you've got iron and, let me do this. Say you've got rusted metal, okay, a rusty nail. A rusty nail does not spontaneously turn into iron and oxygen, right? So if we were to calculate, I never realized how much I depend on being able to write on my screen. But if we were to do this, and I'm not even going to try to balance it, you get the idea. If we were to figure out the delta G value for this reaction, we would find out that it's positive. How do I know that? Because I know that iron doesn't spontaneously break into, rust doesn't spontaneously turn into iron and oxygen. But if I were to flip this over, and if I were to say iron and oxygen turning into iron oxide, which is functionally the same as just flipping the arrow, it is spontaneous. So the big picture then is if we've got rust and iron and oxygen, there's something they always do, iron and oxygen forming rust. There's something they never do, which is iron oxide turning into iron and oxygen. So once you've defined the players, there will always be something they do, and there will always be something they never do. And that's the spontaneous and non-spontaneous direction. You guys okay? Some of you right now are chuckling about do. That was funny. Let's keep going. Okay. So, guys, you all set? You're good? Okay. I am seldom amazed at how easily you guys get distracted. Are you noticing a theme? Never mind. Here we go. All right. I've decided that my job in working with you guys and helping you to be successful is keeping you from getting distracted. It's really starting to take its toll. I'm not going to let you do it anymore. So here we go. So guys, now we're ready to bring this all together and talk about what is free energy. So when you picture this, guys, I would suggest to you that it is as nebulous or abstract as entropy. Some of you are still, and I'm right there with you. There are these moments where I go, what? Disorder? Force driving things? Give me a break. But guys, it gets even worse when you start to think about Gibbs free energy, the product, the sum of entropy and enthalpy. But guys, here's the thing you got to get comfortable with. All of you were really okay with the idea that balls roll downhill, right? And we said that balls roll downhill because they lose energy. And we talked about kinetic and potential energy being interconverted and things like that. But guys, now we're ready to actually say this properly. When balls roll downhill, they lose energy. What energy? Gibbs free energy. That's the complete thought. So if you're comfortable with balls rolling downhill all on their own, if you can just in your brain substitute Gibbs free energy for the idea that energy is being released, I think you can get your arms around this. Now, if you're interested, and the book does a nice job with this, why does Gibbs call this energy free energy? Did any of you read it? Did you notice? No? Do you know what he was doing, Gibbs was doing when this happened? So this was during the Industrial Revolution. And Gibbs was actually an industrialist that was trying to figure out a way to get steam locomotive engines to work more effectively, maximizing his return on investment for coal that he was burning in his locomotives. And so as he was doing all of these calculations, these thermodynamic calculations, what he was doing was he was measuring the amount of energy that a given amount of steam, because that's how these locomotives work, right? Coal boils water, makes steam, pushes the train. And so he was measuring, trying to find a way to quantify the amount of energy in steam that was free to move his train. And so he found out that that was a product of how disordered the steam was and how hot it was. And all of that. So he was looking at how much energy is free to do work. Now apply that to the ball. If you've got a ball at the top of a hill, it can do some work, right? You drop it on your foot and it's going to hurt. Now what if that ball rolls down here? Now when you drop it on your foot, it hurts less because it's got less energy to do work. You get the idea? So that's where this idea of Gibbs free energy comes from, is it's actually the amount of energy that's free to do work, and that's the product of heat and disorder. So that's how this all comes together. So if you think of it like a ball rolling downhill, I think you're in the right track. But regardless of how you wrap your head around this, guys, the idea is this, and I think you're comfortable with it, but let's be sure. If you have a spontaneous process, Gibbs free energy will always decrease. Now, I would suggest that you don't need to write this down, but let's just get it out there. Guys, we can actually calculate the changes in Gibbs free energy, and it's this equation. Looks familiar, right? Yeah, just a little bit, because we've done the delta H that looks like this, and we've done the entropy calculation that looks like this. We can do similar calculations with delta G. It's still products minus reactants. It's still multiplied by the number of moles. The math is all the same, but we can calculate Gibbs free energy changes for processes. We're not going to do it because it's redundant to the calculations that we've done before. What we are going to do is talk about how can we interpret the results of this calculation, and then we're going to talk about this qualitatively to make predictions. And then guys, we're going to be done for the day, which works out great because you can then work on your homework in an environment where you can get your questions answered with the understanding that we're not going to do a lot of question and answer before the test Monday. So let's talk about this. So you do this math, and you will be doing this math in homework. So you do this math, and guys, what happens if delta G ends up being negative? What do you now know? Well, you now know that this reaction favors products, which means it's spontaneous. And if delta G is greater than 0, you know that the reaction favors reactants, which we said earlier means it goes in the other direction. You okay? Sort of a retelling of what we said previously. So again, guys, you will be doing these calculations in homework and probably on the test, but I think they're redundant enough that we don't need to spend time on it. What we really need to talk about now is how does this equation help us focus in on spontaneity, and then specifically, as Carson got us thinking, how do we know when a reaction will be spontaneous? How does temperature play into that? So, questions on the math, or can we go conceptual? Go ahead, just a second, go ahead.
Does that mean that Gibbs free energy is entropy?
No. So Spencer's question was, does that mean Gibbs free energy is being converted into entropy? So Gibbs free energy is like a bucket, if you will. And in that bucket is entropy and enthalpy. And so if Gibbs free energy is changing, whether it's up or down, what is really fundamentally changing is either the entropy or the enthalpy.
So the Gibbs free energy is part of some goal.
Exactly. And so if Gibbs free energy is going up, for example, that could mean that the enthalpy is going up, the heat, or it could mean the entropy is going up. So it's the bucket that includes both. Is that okay? Okay, Carson, hold on a second. Jared.
There's supposed to be the end there.
Yeah, there is, just like the other, right? Again, it's been left out in all the other equations, but just like the other equations, there is an end. Do notice, though, that these are of formation. So these are changes of formation, unlike enthalpies, but unlike entropies. Yeah, go ahead. Into which? Well, that's the whole point, and that's the connection that we don't have to make, is that this Gibbs free energy then is available to do work. But because we've separated work from the conversation, we don't need to make the connection. Do you see what I'm saying?
But it's not like there's some
No, so think about it this way. So Gibbs free energy is the way that we can quantify the amount of energy that's then available to do work. Then we can have an independent conversation about how that work happens, but that's frankly something that we're not going to engage in. When do you start having that conversation? Like PChem? I don't even remember. The reason it's muddled in my head is because I started as an engineering major, and so you take thermal classes as an engineering major where you have those conversations, and it's all a blur now. But you certainly don't through your first couple years of chemistry. PChem, you start playing those games, and then depending on the flavor of engineering you might choose to get into, you'd have it in your thermal classes in engineering. But yeah, but it. Yeah, and those are even more interesting connections to make. But yes, that's true. Yep. You guys okay with sort of the fundamentals? Let's do this then predictively, guys. And it goes like this. I would encourage you not to write this down, just watch. This is now the transition into the conceptual. But guys, it's really just, it's a retelling of this. I wanted to tee this ball up for you early so that we could now have the conversation here. So guys, the bottom line, really what we're going to do is we're going to do this. So here's the idea. When we talk about free energy, we understand that there's an enthalpy term and we understand that there's an entropy term, just like we did here. Here's our enthalpy term, here's our entropy term. Now guys, when we bring these together, we call the sum of them the free energy, where again our enthalpy term, if it's positive, that's endothermic, and if it's negative, that's exothermic. This is all a retelling. And then guys, this is our entropy term, this guy right here. So remember the idea is that it's dependent on absolute temperature, which means Kelvin temperature, which means it's always positive. So if T is always positive, then when delta S is positive, what is this entire term? Negative. And if delta S is negative, then this entire term is positive. Okay, y'all okay with it's again, guys, nothing new compared to this. Okay, now grab this chart. So here we go. You ready? We are now ready to pull all these thoughts together. We are going to do one mathematical thing. So let me set myself up for that, although I'm probably going to regret having erased that, but we'll see. Okay, so now guys, we're ready to break the tie. So let's do, without looking at the table quite yet, let's do this one first. Guys, I'm going to say what reactions, but what is true of a reaction that is always spontaneous? In terms of enthalpy, exothermic. In terms of entropy, disorder goes up. You okay? So the reactions, and we're going to use the word good, the reactions that are always good they release energy, they're exothermic, and they create an increase in disorder. You all right with that idea? So guys, what is the sign of delta H if it's exothermic? Negative. What is the sign of delta S if it always creates an increase in disorder? Positive. Now guys, watch. That's what this is telling you here. If delta H is always negative, and if delta H is negative, and if delta S is positive, that means negative T delta S will be negative, and a negative plus a negative means delta G is always negative, and that bugger is always spontaneous, and there's nothing you can do to change it by changing temperature. It will always be spontaneous. Do you get the idea? So that is pure goodness. It can never be bad. It's always good. You get the idea? Now, guys, let's talk about, it's too bad that Parker's not here. Let's talk about pure evil. You guys know the connection with Parker, right? That we've decided that Riley, his brother, is the embodiment of evil, which makes Parker the brother of Satan. So anyway, never mind. Okay, so pure evil. You ready? So let's do it in this hand. What enthalpy change does not favor spontaneity? Endo or exothermic? Enthalpy. Endothermic. And what is the sign of endothermic? Positive. Now, what entropy change does not favor spontaneity? Disorder, which is negative. So that's our next scenario. If this is positive, endothermic, and if this is negative, decrease in disorder, thereby meaning the negative T delta S, the entropy term is positive, that means delta G has always got to be positive. So that is non-spontaneous at all temperatures. There's nothing we can do to get that reaction to happen. But guess what that means? The opposite reaction does happen. So it's non-spontaneous at all temperatures, but the reverse reaction is always spontaneous. Now guys, let me say this right now. They are not going to get you on that on the AP test. It's an interesting idea that if a reaction is not spontaneous, the reverse reaction is, but I've never seen that come up on an AP test, especially in free response. They may have mentioned it in a multiple choice question where they say the delta G value for this reaction is positive. What can you know is going on? And that would be the reverse process. But anyway, you get the idea? Okay, so now guys, let's talk about the battle between good and evil. You ready? Here we go. If you have a reaction that is exothermic, good or bad? Remember, good is spontaneous. Let's do it again. If you have a reaction that is exothermic, is that good or bad? Good. And what's the sign of that? Negative. Negative, right? Negative exothermic energy out, negative. Now, if you have a reaction that decreases disorder, is that good or bad? That's bad. So now we have the battle between good and evil. And guys, let me zoom into this so we can talk about it more freely. So the idea is this. If we have a reaction that is a negative delta H, that's good, right? Please on your test, don't write good. What is a better way to say a negative delta H is good? A negative delta H favors spontaneity. Guys, that's the way you've got to say it. A negative delta H favors spontaneity. What about a negative delta S? Does that favor spontaneity? No. So here's the idea, guys. You ready? Enthalpy is good, entropy is bad. Entropy change. So the enthalpy change is good, favors spontaneity. In this case, the entropy change is bad, does not favor spontaneity. So if that is true, at what temperatures would you expect this reaction to be spontaneous? Low temperatures. Think about this, guys. If you're writing stuff down, think before you write, because you got to understand this. Here's the idea. Here's the scenario. We have a reaction that's exothermic. Does that favor spontaneity? Yes. We have a reaction that causes a decrease in disorder, decreased entropy. Does that favor spontaneity? No. Now, why would this reaction then be spontaneous at low temperatures? Well, here's the idea. What did we say about our enthalpy change? Does it favor spontaneity? Yes. What did we say about our entropy change? Does it favor spontaneity? No. So here's the idea. This is good and this is bad. But guys, temperature, think of it this way, influences the magnitude of bad. So if delta S is bad, we want to make bad smaller so the reaction can be spontaneous, letting good overcome evil. So to make this smaller and therefore spontaneous, because delta S is bad, low temperatures, if the temperature is low, then the product of this will be smaller, allowing the reaction to be spontaneous. Do you get the idea? So if enthalpy favors spontaneity, and if entropy does not favor spontaneity, by decreasing the influence of this, by dropping the temperature, we can assure that the reaction will be spontaneous. Yes? The overall sign of which? Of this entire thing? And that's the point, because remember, positive is bad, because delta G being negative is good. So if this is positive, and if this is negative, and if this is always positive, if this is negative, my bad. If this is negative, and this is always positive, and if this is negative, so a negative delta S does not favor spontaneity. So if this is negative and there's our negative, that means that the product of this will be positive, and that doesn't favor spontaneity. So we want to decrease the influence of that by dropping the temperature, making the value of this smaller, and making this more likely to be spontaneous. So think about it this way. Guys, what could we do to shut this reaction off? Heat it up. And if we can heat it up enough, we can create such a large decrease in disorder that we can shut the reaction down because it's no longer favored even though it's exothermic. You get the idea? Yeah. It's exactly like mold growing, yeah, because the biologic processes that happen inside of mold, the opposite. It's the opposite. Yeah, no, it's nothing like mold growing. The idea being we understand reactions are temperature sensitive, right? But it would be the opposite, because here we're saying dropping the temperature makes it spontaneous, because this was bad, right? When we talk about the growth of mold, when we drop the temperature, it slows it down, which would be the opposite. Yeah. Exactly. Well, the other side of it is this, and we'll get into this more when we do kinetics. Don't confuse slowing down with shutting off. Okay, what you're talking about is a question of reaction rate. And we can slow down any reaction by cooling it because they collide less frequently. The difference is what we're talking about here is not slowing it, we're talking about stopping it altogether. And that's what we're addressing here. So, yeah. So, guys, let's talk about the other scenario then. You ready? What if we have a reaction that is endothermic? Good or bad? Bad, right? Endothermic does not favor spontaneity. What is the sign of delta H if it's endothermic? Positive. Now, what if we have a reaction that creates an increase in disorder? Good or bad? Good, right? And that would also be positive. That is this scenario, the bottom scenario. So now we've got a positive delta H. Does that favor spontaneity? No. We've got a positive delta S. Does that favor spontaneity? Yeah. So now if we bring that back to here, now our delta H value doesn't favor spontaneity, and our delta S value does favor spontaneity. So what have we got to do to get this reaction to go? Heat it up. Because if we heat it up, it makes good bigger, and a bigger good can overcome the bad and allow the reaction to be spontaneous, even though it's endothermic. That's our quick cold pack. Go ahead. Yep. Okay, yeah. That's our quick cold pack.
How are we increasing temperature on that?
And the answer is it's in the room. So the thought being then this: when you crush that quick cold pack, it happens. And it's happening at room temperature, which means the room, the temperature of the room is the temperature at which yes, but it's a temperature at which this is overcoming that and the reaction is happening. What if we took the quick cold pack and cooled it? Put it in a freezer. I don't know if a freezer would be cold enough, but we could take that quick cold pack and at some temperature we could cool it down enough that when we crush it, nothing happens.
Does that mean they work better at higher temperatures?
Okay, so it depends on what you mean by better. And this is kind of what Jason was getting at. Understand that this is in no way a conversation about rate. Okay? So, yes.
Would that speed up the reaction?
Okay, so I love where you're, let's talk, because it comes back to Jason's thought as well. This is, and guys, please hear this. This is important. There is no such thing as the term more spontaneous. Okay? And that's really where I think the misconception lies. That you can't be more spontaneous at a different temperature. Either you are or you aren't. So as it applies to spontaneity, the idea is that reactions are either spontaneous or not. Later, we'll have the conversation about rates of reaction. And that is a function of temperature. And so we'll get there later. Right now, we're just saying spontaneous or not. We'll talk about the rates later. Yeah.
So, enthalpy is heat from work.
Yes.
And temperature is measured. So if we're increasing the temperature, then
Temperature is a measure of kinetic energy. Heat is a transfer of energy. Temperature is actually a molecular speed. We always think of temperature and heat as being interchangeable. Heat is an exchange of kinetic energy. We'll leave it at that. Heat is an exchange of kinetic energy. Temperature is a measure of how much kinetic energy is present. So temperature is an empirical measurement of how much kinetic energy is there, including mass, and then heat is a measure of how much of that energy is being transferred.
so when we increase the temperature by adding
Doesn't that mean the enthalpy will go up too? Not. The question is when do you say go? Maybe because we're talking about the environment, and the environment is the understood temperature of the system. So you're right that the temperature is affected by a transfer of heat. But what we're saying then is once we get a system to some particular temperature, is it spontaneous? And at that moment, at whatever temperature it is, once it's at that temperature, is it gaining or losing heat, and is it increasing or decreasing entropy? So I understand what you're saying, that to get it to that temperature, we have to add some heat to it, right? We have to allow a heat transfer. Say it's too cold, that we've got to add, through enthalpy or heat, we've got to add energy to it to get it to that temperature. But then the question is, once it's at that temperature, which direction will energy go, and what does it do to disorder? At that given temperature. And this is one of the times, remember when we talked state functions and we said we're not going to do it? Do you remember that? What you're really getting at is really best explained through the concept of state functions, because what we're talking about is, does it matter how you got there, or does it just matter that you're there? And so if something's a state function, it's just something that matters that you're there. And this is one of those things. It's a, are you there? It doesn't matter how you got there, but once you're there, what are you going to do once you're there? The question that you're asking is a question of how you got there. And for this, the thought being that we just sort of start paying attention once we're there. Is that okay? Does that make sense? From that point. Yeah, well, but understand, no, because this is not a change in T, right? There's no delta on this T. Yes, a change in heat, yes, but not a change in temperature. The understanding is we're at that temperature regardless of how we got there. You guys okay? Are we good? Do you understand the predictive nature of this? Okay, so guys, if you do, we need to, I don't have a board. We're going to do this together. So let's do this. I'm just going to make up some numbers. Say that we have a process where A and B are becoming C and D. And they give us some numbers for this process. Delta H is positive. We'll use, no, that's going to make for some really ugly math. Delta H is 10.0 kilojoules per mole. Delta S is let's go, guys, I'm just going to put this in kilojoules, even though a lot of times the answer, no, we're going to do this right. 120 joules per mole. So here's the question. Is the reaction spontaneous? We don't know. How about this? At what conditions would it be spontaneous? That we've got to figure out. So guys, let's talk about it conceptually, then let's do it mathematically, then let's connect the conceptual and the mathematical and actually answer the question. You ready? So first of all, this. Does the enthalpy change for this reaction favor spontaneity? It does not. It's endothermic. Does the entropy change for this process favor spontaneity? It does. It's increasing. So now we would then understand that this reaction would be spontaneous at what temperatures? High or low? High temperatures, because our entropy term contains our temperature term, and if entropy favors spontaneity, in order for this reaction to be spontaneous, we want to emphasize, if you will, that entropy term, and we do that by increasing temperature. Now here's the question. At what temperature range will this reaction then be spontaneous? How do we figure it out? Do you understand the question? We understand it's going to be high temperatures. But what temperatures? Over what range of temperatures will this be spontaneous? How could we figure it out? What could we do to this equation to figure it out? Josh, can you see okay with these angles? Are you good? You're okay? Okay. Guys, what could we do? Yeah? Absolutely, yeah. So we can do it experimentally, right? But let's do it. We can do it mathematically. Go ahead. Okay. So hold on. Let's go. Delta G is equal to delta H minus T delta S. And so you're suggesting set delta G equal to 0. What's magic about 0? It's at equilibrium. So guys, there will be one and only one temperature at which this reaction is at equilibrium. So Caleb, if we can identify the temperature at which this is at equilibrium, then what? Let's do it. Delta H is 10 kilojoules per mole minus X times 120 joules per mole. So guys, how do we solve this? bless you. Guys, this is going to be a mistake that you're gonna make on the test. You are comparing apples and oranges. I know that these look the same, but these are kilojoules and these are joules, and you cannot compute a temperature without addressing the fact that your energy units are not the same. Here's the easiest thing to do. Divide this by 1,000 and make this kilojoules. Here's the beautiful part though. For those of you that don't label your numbers anyway, you'll never catch this and you'll just get it wrong. So we have negative 10.0 kilojoules per mole is equal to negative X times 0.120 kilojoules per mole. Now our kilojoules, oh gosh, no, sorry. This is actually kilojoules per mole Kelvin. Sorry. I forgot that entropy's got a, I'm like, where did the temperature come from? There we go. So then we do the math. And again, guys, I made up these numbers. I don't know what this is going to give us. We'll take that. X is 83.3 Kelvin. Yeah. Again, I made up the numbers, but the principle holds true. So guys, what happens if you do all that math and X is negative? You did something wrong, because that's impossible. This is a Kelvin temperature, it can't be negative. Now, what does this number tell us? Do we now know the answer to the question, at what temperatures is this process spontaneous? No. What happens at 83.3 Kelvin? It's at equilibrium. So how then do we answer the question? Well, guys, the first thing you've got to do is this, and I'm going to tell you right now, a lot of you are going to get this wrong on the test too. You cannot always assume that the range of spontaneity is above this, right? We talked about the idea that for this process, it will be spontaneous at high temperatures. But guys, go back to where we started. What about this tells us it'll be spontaneous at high temperatures? The positive delta S. This is the one that favors spontaneity. It's the one that's good, so we want to make good bigger, so that would be high temperatures. Now guys, what would happen if the sign switched and both of these are negative? Now it would be at low temperatures. So the first thing you've got to do is identify the temperature range. Is it the high ones or the low ones? And again, you do that based upon this table. Now, once you've identified high ones or low ones, the question is then high ones or low ones compared to what? The temperature of equilibrium. So now we know the complete answer. Initially, our problem that we solved, these were both positive. So is this spontaneous at high or low? High. Higher than what? 83.3 K. Now guys, don't say this. You cannot say, and let me figure out how to say this wrong. You cannot say this reaction is spontaneous at any temperature 83.3 or above. Right, so what do they call that about set notation in math? But yeah, so it's not greater than or equal to, it's just greater than. So how would we say that? At any temperature above 83.3. So to be safe, I would write it out as a sentence. This reaction is spontaneous at any temperature above 83.3. Is there a symbol for greater than but not equal to? So temperature greater than, oh, okay, 83. Oh, because it's not this. Okay, so 83.3 K. But guys, my advice to you would be to actually write it out as a sentence. So there you have it, gang. Those are the things that you need to be able to think through relative to this material. I think now the homework will be much more in play for you. You have an amazing opportunity for the next 20 to 25 minutes to actually sort through some of this. Again, we are going to hopefully not answer homework questions at all on Monday. If we do, it'll be very brief. And then, guys, we're going to take the test over this on Monday. So spend your time well. I'd love to help if I can. And let's do it.
Super related to that, but it was talking about how when we were in AP Chem Lab, we were talking about how breaking bonds means that you are absorbing energy
Correct.
and or creating bonds, you're giving off energy.
True.
I was thinking